can start the next talk by Professor Mahan. The second talk is about dimensions 1, 2, 3, 4, and so on. Yeah, please take it away.
Yeah, thanks a lot, Tejas. And yeah, so there was this one question about so which I'll reformulate whether so we talked about classification of surfaces in the previous talk. And so now the question had come up, well, is there a similar classification problem in higher dimensions? Indeed, there are. And we'll come to that today in this talk. But we started with 2. What about dimension 1? And this is really where the story starts. The subject called topology started with one-dimensional objects. Yeah. Okay. So what exactly is one-dimensional? And I'll have to go beyond the notion of manifolds for this. So here is something. So as I mean, you could see that these are stick figures that were drawn by children, and in some sense that, I mean, what as children, things that are played, it's kind of a replication of evolution of, I mean, of us as a species. And so here we have this whole bunch of one-dimensional stick figures. Yeah? Some of these are games, some of these are with matchsticks, and so on. And in societies which are quote unquote more primitive, so this is something like 700 years older than Euler, there was this group of people in an island, Vanuatu, and this came out in Scientific American in November 2023, thereabouts, where people used to draw these one-dimensional figures with patterns, etc., on sand. And this cultural heritage has been declared as this cultural heritage of our species. And so the problem, again, is, okay, so it's very easy to draw a bunch of these one-dimensional figures. How do we understand them? How do we understand, classify, so to speak, these the patterns behind all these one-dimensional objects? Yeah. And we'll come to a theorem of Euler, which basically says that these one-dimensional objects, note that these are not necessarily, what is a manifold? A manifold of dimension k is something that is locally homeomorphic to Rk, yeah, R to the k. In the previous talk, we talked about R to the 2, and we talked about 2 manifolds, also called surfaces. Here you can see that these one-dimensional lines intersect each other at the points of intersection. So if you have 2 sticks intersecting each other and you take the point of intersection, the neighborhood is not homeomorphic to R. Yeah? It's homeomorphic to the union of two axes, x-axis and y-axis, just if you have a single intersection between 2 lines. So there are a larger class of objects beyond manifolds, and people have played with them for a very, very long time. So how are we going to understand these things? And this is the problem that Euler attempted long back. And this is really the problem that gave rise to what we call the field of topology today. So let's draw let's draw a bunch of matchstick figures. Yeah. As I said, these are these experiments or examples in mathematics. But there we can just draw it using pen and paper. And so think of these round blobs as matchstick heads and the black stuff as the sticks. The white inside is essentially some region trapped by these black sticks. Okay, so draw one of these planar figures. So we've drawn one of them here. How many round blobs are there? So you have 4 outside, 4 at the next level, and 1 at the center. So the matchstick figures, we are trying to formalize. We are trying to formalize the structure behind these matchstick figures that we had drawn a whole collection of patterns of in the first slide. And so we are now trying to investigate whether these things have a hidden pattern. Okay, good. So the number of round heads there are 9. Yeah. Number of sticks, it's 4 on the outside square, and then 8 sort of at these angles. So there are these angle of, let's say, 30 degrees on the left and 30 degrees on the right. So there are 2 at the top and 2 at the bottom. So that's another 8. And absolutely in the middle, there are 4 more sticks. So if you count the black sticks, there are 4 and 8, 12, and 4, 16 of them. What about the number of regions? Yeah, the white regions. So you count them again. There's 1, 2, 3, 4 on the outside rim, and then there's 4 inside. So that's 8. Yeah. And then we start seeing that basically if we keep adding on blobs, these round blobs, then the round blobs will keep on increasing. The black sticks will keep on increasing. The white regions will keep on increasing. So how are we going to get something that is unchanging in all of this? And so one plays around. And so you look at the number of these red blobs minus the number of black sticks. And this is after playing around with them for a while. You look at red minus black plus white is 9 minus 16 plus 8. Yeah, that's 17 minus 16. That's 1. Yeah. So here's the thing. This is how you remember. The round things are little like fat points. Points are 0-dimensional objects. So number of 0-dimensional things minus the number of 1-dimensional things plus the number of 2-dimensional things is 1. Okay, good. So now let's go to a slightly more involved matchstick figure. This is essentially a graph which is a 2-dimensional representation of a 3-dimensional object called a dodecahedron. We'll come to it very soon, the actual 3-dimensional object. But here we've drawn a graph again. And now let's do the same count one more time. Yeah. How many round blobs are there? How many black sticks are there? How many regions are there in between? So if you look at the round guys, so the outsidemost layer, there are 5 of them. At the next level, there are 10. And at the middle level, at the central level, there's again another 5. So match heads are 5 plus 10 plus 5 is equal to 20. How many sticks are there? Outsidemost level, there are 5. Next guys leading to the next level, there are 5 more. So that's 10. Next level, there are 10 of them. So 10 and 10, 20. Then going inside, there's another 5. And in the central pentagon, there are still another 5. So that's 5 plus 5 plus 10 plus 5 plus 5, which is 30. How about regions? So you look at the outermost rim, there are 5 of them. The next, there are 5, and there's 1 in the middle. That's 11. Yeah. So again, you see 20 minus 30 plus 11 is equal to 1. Yeah. And so mathematicians give these names. The red blobs are called vertices. The sticks are called edges. And the regions are called faces. This is really an experimental sample of Euler's formula, which is number of vertices minus number of edges plus number of faces is equal to 1. Is there something particular? We have done rather symmetric figures here. Is there more? So since I am in Bombay, I have just taken the map of Bombay here. And let's draw something rather similar. Yeah. So here's on the left side, you have a picture of Bombay. And now we construct a graph. There's a vertex for every region. So every part of Bombay in these different colored shades, there's a vertex. So that the color yellow should not be, it does not code anything. It's basically just to make sure that there's a contrast. Yeah. And so if 2 of these regions adjoin each other, yeah, they have a common edge in between, then you draw an edge between those 2 vertices. Yeah. So from north to east, there is an edge. From north to west, there is an edge. Between east and west, there is an edge. There is no edge between north and harbor suburb, etc., etc. So we draw this graph, yeah, and then we take that graph out, put it on paper, and that's the rightmost thing. How many vertices are there? There's 4 and 1, 5 and 2, 7. Yeah. How many edges are there? 3 and 1, 2, 3, 4, 7, and 2, 9. Number of edges is 9, and number of faces, which means regions, is 1, 2, 3. Again, you do the same calculation, 7 minus 9 plus 3, that's 1. There's nothing particularly special about it. You take any map of any country you like or any state you like, divide it into regions, so long as you only assume that they don't they touch along edges. Yeah. And so if you have for each of these regions, you plonk in a vertex. When there is an edge between two regions, you plonk in an edge, yeah, of the graph. And then you look at this v minus e plus f, and it always equals 1. This is a theorem of Euler, which basically says that if you can draw a graph without edges intersecting each other, basically it means on the plane, and then you do this v minus e plus f count, it's always going to be equal to 1. This is really an invariant, so which means plane, it's really a property of the plane and graphs embedded in it. That gives you this v minus e plus f and gives you a number 1. This is the start of topology. This number is very, very significant. It has further generalizations. Okay, good. Now we started, now let's catch up with the previous talk, dimension 2. And we are going to introduce a similar combinatorial number to it. Okay, good. So what about, let's take any convex polygon and start with the basic observation in planar Euclidean geometry. Yeah. The planar Euclidean geometry, a basic fact is that the external angles of a convex polygon, they always sum up to 360 degrees. And the way it can be proven visually is that you take your convex polygon and then start shrinking it. So that's what this arrow in the picture is supposed to indicate. You start shrinking your polygon till finally it becomes a vertex. Then what is happening is that all the external angles now get arranged around the vertices, around the center of a circle, and the angle at the center of a circle is 360 degrees. Basically says that if you have any convex polygon, then the sum of all external angles is 360 degrees. Okay, good. Now that allows us to compute, in particular, what are the internal angles of a triangle, provided all the sides and all the angles are equal. So what is going to happen is an equilateral triangle, let's say. So how many external angles does it have? It has 3 external angles. Yeah. Sum of all those 3 external angles is going to be equal to 360 degrees. Okay, good. So what is going to be the 360 degrees is going to be 2 into 180. So it's important to think of this as 2 into 180. Why? Because at every vertex, there is an internal angle and there's an external angle. The sum of the internal and external is 180 degrees. So however many vertices are there, yeah, there are 3 vertices in an equilateral triangle. So the total sum of internal and external angles at all 3 vertices is going to be 3 into 180. The external angle sum is always equal to 2 into 180. So the internal angle sum is going to be equal to 3 into 180 minus 2 into 180. So however many sides you have, n into 180 is the total sum of internal and external. External is 2 into 180, always, independent of how many sides you have. And so the inside is going to be n minus 2 whole times 180. So for a triangle, it's 3 minus 2, which is 1, into 180 is the sum of all internal angles. But we've assumed that everything is equal. So that's 1 into 180 divided by 3. So the internal angle of an equilateral triangle is 60 degrees. For a square, do the same thing. 4 sides, 4 minus 2, which is 2 into 180, which is 360 divided by 4, which is 90. For a regular pentagon, it's 5 minus 2, which is 3 into 180 divided by 5, which is 108. So in general, the internal angle sum is n minus 2 times 180, where n is the number of sides. And if you divide by n, that means n minus 2 divided by n, everything into 180 degrees, that's going to give you the angle or the internal angle of a regular n-gon where all angles and all sides are equal. Okay, good. So this is a preliminary computation from planar Euclidean geometry. But we wanted to look at two-dimensional manifolds. And here, this is an introduction to one aspect of geometry, but it's somehow or the other closely interrelated to two topological ideas, which is why we are asking this. And so suppose we have, these are what are called Platonic solids. So the leftmost corner figure is a tetrahedron. Yeah. The big picture behind that is the dodecahedron. Yeah. Then there's a cube, and then there's this bipyramid or octahedron. Yeah. And then behind the most complicated guy, which has 20 faces, that's called an icosahedron. So these are all the what are called Platonic or regular solids. Yeah. So now look at these vertices that are there of all these regular gons, and we want to ask which vertex of these, which vertex is sharper. So is the tetrahedron vertex sharper? Is the cube vertex sharper? Is the dodecahedron vertex sharper? Is the octahedron vertex sharper? Which one is sharper? And how are we going to evaluate that? So which means we have to assign a number, a precise number to these vertices and ask which one of them is sharper. So how are we going to do that? And essentially, we have to basically say, normalize and say, okay, something has zero sharpness. So what has zero sharpness? Something which is flat has zero sharpness, which means if you have a vertex on the flat, on one of these flat surfaces bounding these solids, there is no curvature there. So if you push it against your skin, you will feel no pain at all. There's no sharpness that will be sensed. So the flat total angle of 360 degrees is our reference point, and we call that zero curvature or zero sharpness. The difference between 360 degrees and the sum of the angles is a measure of the sharpness concentrated at a point, and we give it a name. It's called the angle defect. What is it? You basically look at the sum of angles at a vertex, subtract that from 360 degrees, that number in degrees measures the sharpness of a vertex. Yeah, that's our measure, basically normalizing by assuming that something that is flat is something that is flat has zero curvature or zero angle defect. Okay, good. So now we have a notion of sharpness. Good. So now let's do some computations. Okay, good. Let's try to do the computations for some of these simpler things. Yeah. Oh boy, what's happening? Okay, so let's do the computation for a tetrahedron. So this is where the internal angle computation that we did for equilateral triangles is going to play a role. So each face is in an equilateral triangle. Each face of a tetrahedron is an equilateral triangle. Internal angles for each of these vertices is 60 degrees. How many faces are there at a vertex? There are 3 faces at the vertex. So then what is the total angle at vertex? There are 3 faces coming and hitting a particular vertex. So 3 into 60 degrees, which is 180 degrees. So then the sharpness at a vertex is 360 minus 180 is equal to 180. Yeah. So total angle defect at a vertex is 360 minus 180 into 180. Okay. And just for fun, let's ask, what is the total sharpness, which means sharpness at all the vertices added together? What is the total amount of sharpness? Sharpness at one vertex was 180 degrees worth of sharpness. Yeah, 360 minus 3 into 60, which is 180. But what is the total amount of sharpness? There are 4 vertices, so 4 into 180. So there's 720 degrees worth of sharpness for the tetrahedron. Good. One simple computation done. Let's do some more. Let's look at the cube. Each face is a square. What is the internal angle? 90 degrees. How many faces at a vertex? 3. So total angle at a vertex is 3 into 90, which is 270. What is the sharpness at the vertex, which is the angle defect? Is 360 minus 270, which is 90. How many vertices are there? 8. So total sharpness, 8 into 90, 720. Exactly what was true for the previous guy. So the total sharpness for a tetrahedron, it has smaller number of vertices, but more sharpness at a vertex. Somehow it balances out. And the same thing happens for a cube. Let's do the same thing now for a dodecahedron. Yeah? Each face is what? It's a regular pentagon. And we had computed the internal angle. How much was it? It was 108 degrees. How many faces are there to a vertex? 3. So total angle at a vertex is 3 into 108, which is 324. Sharpness at a vertex is the angle defect, which is 360 minus 324, which is what? Which is 36. How many vertices are there? Just count 5, 5, 5, 5. There are 20 vertices. This refers back to that graph that we had drawn, which was a planar representation of this dodecahedron as a planar graph. There were 20 vertices. So what is the total sharpness? 20 into 36, again 720. So this is doing something in 2 dimensions. And here's what's called the Gauss-Bonnet theorem. What does it say? Given any convex polyhedron, you look at the sum of all the sharpnesses, curvature, yeah, over all vertices. And that's always equal to 4 into 180 degrees, which is 720 degrees. Yeah. So this is a polyhedral version of the Gauss-Bonnet theorem, which basically says that for something which is just a convex polyhedron, the sum of the sharpness, the sharpness at individual vertices might change, but the sum of all the sharpness is equal to 720 degrees. The fact is that this is not something that is special to regular polyhedra. It is true for irregular solids as well. All you need to do is you can take one of these convex polyhedra and you can divide it into tetrahedra, not necessarily regular. And the fact is that for a tetrahedron, it's not hard to compute that what is going to be the total angle defect is going to be sum of the angles at a vertex summed over all the vertices, which means basically it's going to be the sum of the angles of the faces, which is 4 into 180 degrees. And the angle turns out to be, therefore the angle defect is going to be turn out to be equal to 720 degrees. So this is a nice exercise. Go back and compute the total angle defect, but now not of the regular tetrahedron, but for an arbitrary tetrahedron, and you'll get the same answer. And the fact is that this Gauss-Bonnet theorem can really now be proven because you've gotten it for the building block, namely the tetrahedron. Now you build all kinds of convex solids out of tetrahedra and compute the angle defect, and you'll be able to prove the Gauss-Bonnet theorem for arbitrary complex polyhedra. So this number, what did we get? So we had this V minus E plus F is equal to 1 for graphs. Yeah. So if where we excluded the external face, but here the boundary of a convex polyhedron is a 2-sphere, is an S2. Yeah. Just blow this all up and you'll get a round sphere. This is a continuous deformation that we can do. And so if the boundary of a convex polyhedron is really a homeomorphic to a 2-sphere, so if you have a polyhedron which is homeomorphic to the 2-sphere, what are we getting? We are getting one external face as well. So V minus E plus F was equal to 1 for all internal faces. Add on the external face, which includes infinity. So then for this closed object on a 2-sphere, you're going to get V minus E plus F is equal to 2. That number is called the Euler characteristic of the sphere, just as the Euler characteristic of the plane was 1. So Euler characteristic of the sphere is 2. And what you're getting is 2 into 360 degrees is equal to, the Euler characteristic into 360 degrees is equal to the total sum of sharpnesses there. And Gauss-Bonnet theorem, the classical Gauss-Bonnet theorem, essentially gives you a version of this where you don't really divide it into polyhedra, but you allow smooth surfaces, and then you really have to, instead of a sum, you have to do an integral, and there's a way of defining curvature at points, and you integrate out the curvature over all points, and what you're going to get is basically 4 times pi. Yeah, so 2 pi is 360 degrees. So 2 is the Euler characteristic. So 2 pi times the Euler characteristic is what you're going to get for spheres. So this is the classical Gauss-Bonnet theorem. It's essentially 19th century. Gauss was early 19th century. Bonnet was later. But yeah, I mean, so this is a basic fundamental theorem. Now we start addressing the question that was posed a little earlier. And the rest of this talk is going to what I'm going to give you. I mean, I think I have about a little more than half an hour left. We are going to address this question of, are there analogous problems in higher dimensions? And it's not going to be possible for me to give you proper proofs, or so what I'll try to do is give you more of an impressionistic survey of what's going on. So here's the thing. This number, V minus E plus F, this generalizes to higher dimensions without a hitch. Yeah. V is vertices, 0-dimensional objects. E is edges, 1-dimensional objects. F is faces, 2-dimensional objects. So you're going to look at what is called an alternating sum. 0 minus 1 plus 2 minus 3 plus 4 minus 5, etc., 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 for any n-dimensional object. And this alternating sum has a name. It's called the Euler characteristic because Euler is the first person who did it inside dimension 2. So this part gives something that is a number associated to any object which is built out of polyhedra. Yeah, that has a formal name. It's called a simplicial complex or cell complex, etc., etc. And then you can do this kind of a sum locally, and you get what is called the Chern-Gauss-Bonnet theorem. And we have now fast forwarded from the 19th century to the middle of the, just a little before the middle of the 20th century. And the Chern-Gauss-Bonnet theorem basically says that this number, the Euler characteristic times something, is an integral of a number which can be assigned locally. Yeah. So what have we done so far? We started with children's stick toys. And historically, there were these sand drawings. By the way, the spelling is not a mistake. That's how they are. That's how it's spelled. Yeah, sand drawings are put together, and it's called sand drawings in this particular sense. And then from these physical objects, you map to mathematical graphs, networks, polyhedra, complex multidimensional shapes. And what we have tried to say is that this geometry and topology actually gives you a unified picture. So where is the geometry here? The curvature concentrated at a point is a local feature that is geometric. The sum of all those things is invariant for things which are homeomorphic. So it's so that's a topological invariant, yeah, which means basically it's invariant under continuous deformations under homeomorphisms. Yeah. So though the curvature at a point, yeah, the sharpness at a point changes from polyhedral to polyhedral, the sum does not change. The sum is a topological invariant, but the local object is only something that is geometric. Okay, so this is one bit of an answer to this question that was posed about, are there higher dimensional generalizations of this classification? So you get numbers. You do get numbers. What happened in 2 dimensions is that 2-dimensional surfaces are classified by this number, and then 2 minus 2 times the number of handles that has this name. It's called the Euler characteristic. And so what basically said, the previous talk said was that surfaces are classified by number of handles, and then 2 minus 2 times the number of handles has this name. It's called the Euler characteristic. So equivalently, all closed orientable surfaces are classified by their Euler characteristic, a single number. What the Chern-Gauss-Bonnet theorem basically says is that for higher dimensional manifolds, you can assign such an integer, which is a generalization of the Euler characteristic. The question remains, if you have 2 manifolds, are these numbers in 2 dimensions? There was a theorem which said that these numbers define dockets precisely. But what about higher dimensions? Can there be 2 higher dimensional manifolds which are not homeomorphic but have the same Euler characteristic? The answer, unfortunately, is yes. So Euler characteristic, which does classify manifolds in dimension 2, is not enough to classify manifolds in higher dimensions. Here's a simple thing. Take any closed odd dimensional manifold. For example, take any 3-dimensional manifold, locally R3, yeah, and closed. Euler characteristic is always 0. Same for all closed odd dimensional manifolds. Euler characteristic is always 0. So for odd dimensions, Euler characteristic is completely useless to classify manifolds. In even dimensions, it's useful, but limited, because given an Euler characteristic, there will be typically many manifolds of the same even dimension greater than 2, which are homomorphic to each other, which are not homomorphic to each other, but have the same Euler characteristic. Okay, good. Let's proceed.
So Mahan, there are
So
a few
now
questions. There are a few
sure.
questions in the chat before you move on.
Yeah. What role does convexity play in the Gauss-Bonnet theorem? If the polyhedron that I am considering is non-convex, then will it be true? Answer, yes. Answer, yes. And the thing is, it's basically you remove from a convex polyhedron a convex subset, and that's what it is. Is this 4 pi I related to surface area also somehow? Yes. The answer is yes. The answer is yes. What is being done is basically you're looking at the curvature and you're integrating it over the surface. Yeah. So when you're integrating over a surface and you look at what is the curvature for a round 2 sphere of radius 1, it's +1. So you integrate +1 over a surface, over the base sphere of area 4 pi, and you're going to get 4 pi times 1 throughout, because you're integrating a constant function, and so you're going to get 4 pi. So what I have given here is a polyhedral notion. Yeah. If you go to the integral model, that area is going to come up in a very essential way. Suppose in an irregular polyhedron, we have a vertex that doesn't point outward, but inward. This is basically the concave polyhedron part of it. There are also the same thing holds. Okay, so I think we've answered all the questions.
On YouTube, there's a question. What does Euler characteristic signify for a surface?
Euler characteristic for a surface, I have said that it's vertices minus edges plus faces. That's what is V minus E plus F, that number. It's an invariant of the, if 2 surfaces are homeomorphic, they have the same Euler characteristic. Yeah. And the Gauss-Bonnet basic theorem, here is what we will try to generalize that. So just hold on a minute. So given what we have said, we are restricting to convexity for convenience. It's not really important. Recall, and here for a torus, you cannot really demand convexity all the time. It's going to turn out to be the case. So given any convex polyhedron, what we've said, established, is that the sum of the sharpnesses, the sharpness has a mathematical name, it's called curvature, over all vertices is 4 pi, which is 720 degrees. What about other surfaces with polygonal faces? And now we are removing convexity altogether. Suppose the underlying 2 manifold is a torus, It turns out that the Euler characteristic is 0. Yeah, V minus E plus F is equal to 0. Yeah, the bicycle tube, you can check, it has V minus E plus F is equal to 0. Why? Because you punch out 2 holes and glue in an annulus. If you punch out 2 holes, you're removing stuff with Euler characteristic 1 for each disk. So 2 minus 2 is 0 is the Euler characteristic of a cylinder. You take at the boundary of the cylinder is a circle which also has Euler characteristic 0. So you glue 2 things with Euler characteristic 0, you get back 0. So the Euler characteristic, this is 0. And so if you look at the sum of the angle defects, the general Gauss-Bonnet theorem, it's hinting at something. It's basically saying that here also you're going to get this earlier Gauss-Bonnet theorem, which was 2 pi times the Euler characteristic of the sphere. Here also it matches up. For the torus, the Euler characteristic is 0. The integral of the total curvature sum is also 0, which means that there will be points where the angle defect is going to be equal to something that is less than 0, which means that the total angle around that vertex is going to exceed 4 pi. Yeah, is going to exceed 2 pi. Yeah, so remember that the angle defect was 2 pi or 360 degrees minus the sum of the angles. And here, the Euler characteristic is 0. So which means basically sum of positive and negative. Sum of positives will never give you something that is 0. So some places there will have to be something negative. And it's a fact that if you have a polyhedral surface, which is homeomorphic to a torus, then there will have to be, this is basically a proof, the Gauss-Bonnet is going to give you a proof that the sum of the angles around a vertex somewhere or the other has to be negative. And if you look at this particular picture, you look at the vertices on the inner rim, yeah? And there you will see that there is actually stuff that is folding in on itself. The sum of the angle there is actually less than, actually greater than 360 degrees. So the angle defect is less than 0. So this is the Gauss-Bonnet formula, and it actually does generalize to something that is beyond. Okay, hang on, I'm having some. Okay, good. So okay, so this was the Gauss-Bonnet formula, and let me just summarize what we did in the previous lecture. We proved that we basically said that any closed orientable surface is homomorphic to a sphere with G handles. Yeah. So the sphere, round sphere, 0 handles, torus, 1 handle. The picture on the left bottom is 2 handles. And here's the picture from the previous lecture, teapot with 3 handles, that's genus 3 handles. Yeah. And here's the general Gauss-Bonnet theorem. If you look at, for all of these, if you put a polyhedral structure and you sum the curvatures together, that's equal to 2 pi times the Euler characteristic. And the Euler characteristic for a genus G object, as we have said, is 2 minus 2G. So here's the general 2-dimensional Gauss-Bonnet theorem. The total sum of curvatures with sign is equal to 2 pi times the Euler characteristic. Are there any other questions? Or you've taken care of them? Yeah. Okay. So this is the general theorem here, that the Gauss-Bonnet theorem is essentially something that goes through for all surfaces. And for polyhedra, you look at sum. If you are in a continuous surface, smooth surface, then you look at the integral of curvature times the area, integral over the area, and then you're going to get 2 pi times the Euler characteristic. Oh boy. Yeah, okay, good. Let's see. So how to prove this theorem, which states any closed orientable surface is homomorphic to sphere with G handles? We can get Euler characteristic of torus from a sphere because for sphere it is 2. We can get torus from sphere removing 2 faces from top and bottom. Yeah, that's what I said, but it's not just removing discs from the top and bottom. You have to glue in another one. Yeah. The top and bottom have to be glued after that. Yeah, so it's basically, you can punch out, you can take a disc, punch out just the top and bottom, you're going to get a cylinder, something homomorphic to a cylinder. You take 2 of these cylinders and glue them, then you're going to get a torus. Now, this is a good question, good, fantastic question, how to prove this theorem. Yeah. This would be a completely I mean, one talk in itself and a lot of background would be required. I would strongly suggest that you look at, there's a book by Munkres, First Course in Topology. Towards the end, where he does surface topology, you would be able to get a proof of the classification of surfaces, 19th century. Roughly, the idea is this: you arrange the surface so that it sits vertically, and you remove a point, so there's a unique maximum, unique minimum, and then you start flowing things. What happens is that every time when you start flowing things, what you're doing is you start off with a disk, and then you attach handles, one handles to it. And every time you attach a one handle, you're going to change your Euler characteristic. Once you do this carefully, you get that the number of handles that you attach is the negative number, and you have a plus at the top, which is for the 2 cell, a plus at the bottom, that's for the 0 cell. So that's 2 and 1 for every handle that you've attached. And the handles come in canceling pairs. So that turns out to be the genus. So for each handle there are 2 of these guys. So that's 2 minus 2 times the number of times you have attached handles. So that's 2 minus 2 times the handle. So that's a very, very fast 3-minute summary of the proof of classification of surfaces. Reference is Munkres's Introduction to Topology. And here now let's get back to the Gauss-Barnett theorem, which basically says that the sum of the curvatures, and in a more general smooth setup, integral of curvatures is 2 pi times the Euler characteristic. Okay, good. So for genus 0, which was the sphere, 2 minus 2g is greater than 0. For genus equal to 1, one handle, which is the torus, it's 2 minus 2 into 1, which is 0. And for g greater than 1, that means 2 handles, 3 handles, 4 handles, etc., etc., this Euler characteristic turns out to be negative. It's 2 minus 2 times g. And now we are asking for, well, what is the best possible metric that you can put? Which means, see, we started with a polyhedral metric, right? That's where we started everything. And then I've made some noises about it could be a smooth surface. The best metric here is essentially a hint at something where curvature is distributed uniformly, not concentrated at vertices. So you start with a polyhedral metric where you have finitely many vertices, sharp points where all the curvature is concentrated. And can you smear this? Can you distribute this curvature till it is uniform all over the place? This has a name. This procedure has a name. It's called the Ricci flow. In physics, there is an analog. It's called the renormalization group flow. There's an analog which is called the renormalization group flow in physics. As I said, I will just give you some indications of what are the avenues that appear from here. I mean, this is classic 20th century, 19th century, and then Ricci developed this differential equation, which is essentially a version of heat flow. See, heat, essentially, if you have a point where you have a concentrated heat source and then you remove it, what happens is that the heat starts distributing itself over the surface till it becomes uniformly distributed. You're trying to do the same thing with curvature here, and the right setup is what is called Ricci flow. Okay, good. Okay, so here is the basic theorem. Again, this is late 19th century. It's called the Poincaré-Quebec-Klein uniformization theorem. See, we talked about the topological classification of closed orientable two manifolds. Now we are asking for a geometric description, which means this curvature was some sharpness associated. We found the Gauss-Barnett theorem, which says that the total amount of curvature, which is the integral of the curvature, is actually something that is uniformly distributed all over. And the question was, can you do this? process. Can the curvature be distributed democratically all over the surface? The answer is given affirmatively in the 19th century, and basically says that you take any closed orientable two-manifold, also known as a surface, it does admit a metric of constant curvature, which means no point can be distinguished from any other point. That means all points are equally sharp. And there is a relatively recent proof which starts with a polyhedral metric and then runs Ricci flow, distribution of curvature all over, and then that converges to a metric of constant curvature everywhere. So for genus equal to 0, the Euler characteristic is +2, and so the curvature that you have to get is positive, and you can get a positive curvature +1. For a torus, you can run this Ricci flow because the Euler characteristic is 0, the constant curvature is going to be 0. For G greater than 1, it has to be constant negative, so it does admit a metric of constant negative curvature -1. And so I'm rephrasing the question that was asked in the previous lecture. What did we do? We classified. In the previous lecture, we had classified two manifolds topologically. I have just now said that there is a best possible metric for all of these two-dimensional surfaces. They have constant curvatures. Now, the problem that was phrased last time is on the chat was, can we classify manifolds in higher dimensions? So that's what the first problem is. This is topological problem. Classify closed orientable manifolds in dimensions 3, 4, etc., etc. So we have finished the 1, 2 of the title of the talk, and we are getting into 3, 4, dot, dot, dot. Yeah. And here are these two problems, simultaneous problems. One is, can we classify manifolds? And the second problem is, well, we not only classified them topologically, but we also found best metrics. Can we do a geometric version of this problem? Can we find best metrics? Okay. And here is the point, the unfortunate part of the story is that in a very, very precise sense, the classification is impossible in dimension 4 and higher. Why? And now I will actually have to draw from some expertise. And as I said, this last 15 minutes is going to be a taste of what is the kind of topology that is really done and is being done today. So I'll have to assume a little more background than I have assumed so far. So now look at what is called a finitely presented group, which means there are finitely many generators, G1 through Gn, and there are finitely many relations, R1 through Rs. It basically says that you look at the free group on n generators, and you look at the normal subgroup generated by R1 through Rs, and look at the quotient group. That's this group G. And it's a classical 40s, 50s theorem which says that any finitely presented group can be realized as the fundamental group of a two-dimensional complex. What does that mean? There's a loop for each generator and a cell for each relator. You take this two-dimensional complex and you can embed it in Euclidean n space. It's possible for n greater than or equal to 5. And this 5 is crucial. 2 into n, I mean, any dimension can be embedded in 2n plus 1. That's a theorem of Whitney. So once you embed it in dimension 5, take a thickening of the complex. Yeah. And so you get an n-dimensional manifold. Look at its boundary. That's a 4-dimensional manifold now. Yes, you embedded it in 5, you've thickened your 2 complex, you've looked at this boundary. It's a 4-dimensional manifold now. So then the fundamental group of the complex, which is the same as the fundamental group of the thickening, is the fundamental group of the boundary, and it turns out to be the same as G. And now we have converted a problem of classification of manifolds, continuous objects. If the classification of manifolds was solvable, then we would be able to classify fundamental groups, these algebraic objects. Yeah. And here's the basic theorem. It says that in this very precise sense of of formal computer science, a classification problem is unsolvable in the sense that you would be able to say when a Turing machine, yeah, this is essentially a tape which reads zeros and ones and either moves forward or moves backward. You can feed it an algorithm, and the Turing machine is supposed to halt if the algorithm has churned out some answer. And the way this is really done is essentially you say that you look at all the countably many algorithms in the universe. And if there is a universal Turing machine, then it will take any algorithm as an input and will be able to say whether it halts or does not halt. Yeah. And what this basic theorem basically says that the classification of finitely presented groups, if you can solve that, you'll be able to prove the Turing machine when it halts, when it does not halt. And that is essentially the unsolvability of the problem. Okay? So there's some very formal computer science, theoretical computer science sense in which this is done. Okay, good. So 4 dimensions and above, not solvable. Good. What about 3 manifolds between 2 and 3? 2 classified in the 19th century. 4 and above, not classifiable. What about 3? So this is the last frontier. Let me see. Yeah. Okay, by a thicker. Okay, good. Okay, so these are all being taken care of. So what we want is a classification problem solved. So there are going to be infinitely many. These are 4 samples of pictures of classifications of the animal kingdom, yeah, or the animal and plant kingdom, yeah. Can we set up this kind of a classification theorem for 3 manifolds? That was the last hope, yeah. And can 3 manifolds be at all classified was then the remaining question. We have the answer for 2, yes. We have the answer for 4 and above, no. What about 3? And in 3 dimensions, these 2 questions that I had posed, oops, let me see. These 2 questions, first topological problem, classify manifolds in dimension. Now, 4, we know the answer, not possible. So classify manifolds in dimension 3, and problem 2, find best matrix. Yeah. These 2 problems seem to be closely related. And here, in this slide, I'll give you how this was done as a historical survey, no mathematics. The answer, fortunately, is yes. There is a classification possible. However, you have to get this harder question answered. You need to find the best geometries in order to get at a proper classification problem. So instead of looking at classification of topological structures, you look at the classification of the geometry. This is an a priori harder geometry problem, but it is necessary. And the framing of the problem in this form, it was a conjecture by Bill Thurston, who was mentioned at the beginning of the previous talk in 1982, where he proposed a question called the geometrization conjecture, which basically says that take any 3-dimensional closed manifold, there is a way to first decompose it along 2-dimensional spheres, which is a well-known classical 40s, 50s theorem. Then there is a way of decomposing it along tori. Remember that there were these 2 exceptional manifolds in dimension 2. The 2-sphere has curvature 1, and the torus has curvature 0. Everything else is negative, constant -1. So these two manifolds have to be treated specially when you're doing dimension 3. So you remove and ignore, find a systematic way of ignoring 2 spheres and 2 tori in your dimension 3 manifold. And this decomposition, the first one is called the sphere or Grushko decomposition, and the second is called the torus or JSJ decomposition. This was classical. So you run this topological machine, which is easy, pretty easy, well known in the late 70s. And then what Thurston says is each of the remaining pieces has to come from one of 8 standard geometries. Dimension 2, the classification +1, 0, -1. Spherical, flat, and what's called hyperbolic. Yeah? This is a precursor of what's going to happen tomorrow. Tomorrow's first talk is I'm going to introduce hyperbolic geometry because it's the general kind of thing. So Thurston, in dimension 3, you have not just these 3. There are analogs of this +1, 0, and -1, but there are more. Yeah? And so it turns out there are 8 standard geometries in dimension 3. And what Thurston conjectured in his what's called the geometrization conjecture was that after this decomposition by spheres and tori, each piece fits into exactly one of these geometries. And once you fit it into geometries, then the manifolds start getting completely represented by their fundamental groups. And under these special assumptions of these geometric structures, fundamental groups are classifiable. All finitely presented groups are not classifiable, as we pointed out. But once you have extra geometric input, which tells you, this is called an oracle in computer science. It tells you that the fundamental group has to have such and such, such and such, such and such restrictions. And it turns out that under those restrictions, finitely presented groups are classifiable. Therefore, 3 manifolds could be classified provided the geometrization conjecture is true. And this was a remarkable theorem. I mean, perhaps, yeah, it's the only millennium problem that has been solved. Grisha Perelman, the person, so the conjecture, the first conjecture, which basically says that if you have a simply connected closed 3 manifold, its fundamental group, it has to be homeomorphic to the 3 sphere. This is a conjecture called the Poincare conjecture. This is the gentleman on the left is Poincare. This was generalized, and you got this larger framework of the geometrization conjecture by Thurston, the spectacled person at the right top. And the solution is due to Grisha Perelman, the only color photo here, who solved it using Ricci flow distribution of curvature to get at uniform curvatures. And he basically solved it in the early 2000s with his final paper came out, preprint came out in 2004. So in particular, the Poincare conjecture is true. So now you have 3 manifolds. We have now a complete classification, but there's a rich intersection and rich interplay of different structures that come and play their role here. There are all these extra structures, hyperbolic structures, Euclidean structures, spherical structures, but then there are decorations. There are codimension 1 structures called foliations and incompressible surfaces. There are ways of combinatorially making it solvable called cubulated manifolds, and so on. So 3 manifolds today, once we have a classification in terms of geometric structures of constant curvature, there are other finer, more sophisticated geometric structures called, say, for example, contact structures, etc., which are, it's ongoing work, and some of these are essentially trying to understand the generic object in this context is a closed hyperbolic 3 manifold, and understanding structures for those is an ongoing project. Yeah. So I'll stop here. Thank you very much.
Yeah, thank you, Mahan. It's an excellent talk. Are there any questions? On the YouTube live as well, if there are any questions, please post it in the chat. So I had a quick question. So when you had your group and you got Kg and then you thickened it to this Mg, and then you said the fundamental group of Mg is the same as the fundamental group of its boundary. Is that because if I remove a point from its area, then a deformation retracts to the boundary?
That's correct.
Okay.
That's correct.
Any other questions?
Sir, I also wanted to ask one. So I don't know much about this. So like there is another problem, right? To classify what all are smooth structures, right?
Smooth
So
structures are a problem in dimension 4, and in a fairly precise sense, that seems to be a really hard, intractable question. If you want to understand all smooth structures on all 4 manifolds, firstly, 4 manifolds cannot be topologically classified.
mm,
So therefore, you have to restrict to something where the fundamental group is controlled. And so the real problem becomes classify simply connected 4 manifolds up to homeomorphism. That problem was solved. Another Fields medal. So, by the way, Thurston is a Fields medal for solving a huge chunk of the geometrization in 82, and he got it in 83. Perelman got it in 2004 and refused the Fields medal. Oh, sorry, 2006, yeah. 2004 is when he solved the problem. 2006 is when he got it, but refused the Fields medal. The question you're asking now, the topological classification of 4 manifolds, simply connected 4 manifolds, that's due to Friedman, and he got a Fields medal for it in 86. Yeah. And then in the same year, 86, Donaldson came up with exotic smooth structures on R4, and that became a whole thing unto itself, basically classifies smooth structures on simply connected 4 manifolds. Yeah. And Friedman's theorem and Donaldson's theorem together say that there are exotic structures on some simply connected 4 manifolds. But what are they? The full classification still resists. And there is a version of the Poincare conjecture in dimension 4, which is still open. Does S4, the sphere in 4 dimensions, does it admit a unique smooth structure, or are there more than one smooth structure for S4? That's the last bit of the Poincare conjecture that's still left. Yeah. The smooth Poincare conjecture in dimension 4.
thank you, sir.
Maybe I can add. So Akash, you recently studied the Schoenflies theorem, right? So which is
Yes, sir.
embedded S2s and S3. So the smooth version of Schoenflies in dimension 4 is also still open, which means
Yeah.
if you have
Oh,
These are equivalent, actually. I mean, if you can
hmm,
yeah,
solve the smooth Schoenflies, you will be able to solve the smooth
yeah.
Poincare conjecture.
thank you, sir.
So there are some questions on YouTube Live. I'll just read them out. Is there any research going on the interface of topology and number theory?
Of course, what's called arithmetic manifolds. So essentially, here's the thing. What is arithmetic manifold? What is arithmetic? From a geometric point of view, what is arithmetic? Z in R is arithmetic. Yeah. Now you look at SLN Z in SLN R. That is arithmetic. Yeah. So now you look at the quotient of SLN R mod SLN Z. That is what is a prototype for an arithmetic manifold. Yeah. And then there is a way of looking at what's called a symmetric space for SLNR. And then you look at totally geodesic submanifolds of those. That's the entire class of objects called arithmetic manifolds. Yeah. Or arithmetic groups in the context of algebraic groups. Yeah. So, and the thing is, in this particular context, this arithmetic, the group and the manifold are kind of interchangeable. One is a quotient of a standard space by the group. So yeah, I mean the zillions and zillions of here's a basic question which would yield remarkable consequences. I'll just put out the words here. Take a discrete subgroup of let's make it concrete. Let's take a discrete subgroup of SL2R, 2 cross 2 real matrices. All that you require is that it does not fix a line or a point on the boundary of its symmetric space, which is a hyperbolic plane. You'll learn about that tomorrow. Look at the collection of elements in SL2R, which is what's called commensurate this subgroup. That means the subgroup, if it's called H, then look at H intersection H conjugated by G. Yeah. And if that's of finite index in both H and H to the G, it's called a commensuration of H. Basic question, if you have one of these discrete subgroups H, which is generic, then is the commensurator discrete? We don't know. This is exactly at the interface of topology and number theory. It's essentially trying to ask whether you can characterize arithmeticity by topological means. Another Fields medalist, Margulis, actually did succeed under additional assumptions on H in the special case where the quotient of SL2R by the subgroup H has finite volume. Yeah. Okay, there's another question here. Sir, you said that if we put some restriction on the classification of finitely presented group, it can be done. So is it possible to classify a certain category of closed surfaces? What is surfaces are two-dimensional objects. Here we are not talking about classification of surfaces. We are trying to classify four-dimensional manifolds themselves. Yeah. And what we proved was that four-dimensional manifolds cannot be classified. Yeah. But if you look at four-dimensional manifolds with specific fundamental group, in particular, if the fundamental group is trivial, as I said, Friedman's theorem, for which he won the Fields Medal, classifies them. Yeah. Topological manifolds in dimension 4, which are simply connected or have simple enough fundamental group, can be classified. That's Friedman's theorem.
On YouTube, there's a question. In a recent talk of yours on YouTube, I learned percolation theory on groups. It is relevant. I mean, is it relevant to low-dimensional topology?
You missed out the key word there. It's percolation on hyperbolic groups. The hyperbolic group is actually what is it's a part of aspect of what is called geometric group theory, and that hyperbolic groups are extremely relevant. This classification that I just now mentioned is really the statement that the isomorphism problem for finitely presented groups is solvable when you restrict to hyperbolic groups. In particular, fundamental groups of closed hyperbolic free manifolds are hyperbolic groups, so the problem is solved. That's the connection.
Another question on YouTube. Why is supersymmetry of interest to geometers today?
I have no idea. Okay, so that's a facetious answer. So the point is, I don't know whether supersymmetry is of interest to geometers or not. There are other kinds of symmetry, more classical, called mirror symmetry, for instance, that gives you a relation in a particular class of six-dimensional manifolds, which relates Betti numbers. So these are refinements of the Euler characteristic. Alternating sum of the Betti numbers is what's called the Euler characteristic. That gives you a new additional relation between Betti numbers for what are called Calabi-Yau manifolds. Yeah. So where did this come from? It's somehow or the other the physicists came up with these relations. And what is the mathematical explanation? That's an ongoing project. Yeah. So mirror symmetry and certain other symmetries that physicists came up in certain particular examples using supersymmetric considerations. Yeah. But as mathematicians, that's not the route we take. But the physicists have given us some examples where there are some new symmetries. What are we going to do with them? Can we find a mathematical explanation for them? Purely from within mathematics? That's the question. So supersymmetry is really a tool for physicists, and they come up, I mean, they understand what it really means to them. We don't. But there are outputs of that, yeah, supersymmetric field theories. Yeah. And then they have certain outputs, and that gives rise to conjectures in mathematics, which can now be attempted purely from a mathematical point of view. Yeah. I mean, the point really is the following. See, in Newton's time, there was one subject called natural philosophy. Why? Because there weren't so many branches of science, and each person could actually embrace a substantial part of science, or what we call natural philosophy. With further and further development, there's finally the limitation of our human brain, which can only understand a limited part of it. So we create divisions, and with all these techniques, So there's something called physics, something called mathematics, something called theoretical physics, something called experimental physics. Within mathematics, there is number theory, there's algebra, there's topology, there's geometry, etc., 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 etc. We do stuff according to our tastes and then understand as much of it or as little of it as we can. Yeah. So looking at these boundaries as cast in stone is not a good idea. As an attitude, that's all. That means four-dimensional space can be handled easily if we talk about hyperbolic. Yes, I mean handled easily in the sense that the classification problem will be solvable. But understanding closed hyperbolic four manifolds in a satisfactory way, I don't think we are there yet, basically because we don't know enough examples. General structure is not there. Three-dimensional techniques don't work.
Is there any nice representation of the isometries of H4 in some linear group?
SON1. So all the hyperbolic N guys is SON1. Yeah.
Okay.
Yeah.
Conformal maps. Okay.
Okay, great. Thanks.
Yeah. Okay. So
tomorrow
thanks,
tomorrow
Mahan.
at 10 o'clock? Yeah.
Yeah, they were really good lectures. I quite enjoyed them.
Thank
And
you.
thanks a
Very
lot
good.
for
Okay.
giving them. I think Anisa would like to say a few words.
Right. Yeah. Thanks to Mahan and Tejas. And thanks also to Shauli for joining us.